Well, thank you for giving me the opportunity to talk today. My name is Mauro, and I will present today a Python library for the clinical quality of measurement assessment. And Python is a well-known language, especially in the field of data science, but it relies on the efforts of the user to create a specific library to solve a data science task. So here we try to develop a Python function able to tackle the quality of measurement, especially a topic important in the biomedical field. So in the standard comparative statistical test, we usually have a p-value that tells us the significant difference between two groups. But in equivalent testing, for example, we want to know if a new and the old laboratory system are interchangeable. We have to reverse the null hypothesis and test of no difference between measurements. So these are statistical tests that are another family of tests in comparison to the classical statistical inference. So the library, it is on GitHub, and today it is organized on folders, and today I'm going to explain you each folder and the main functionalities. Unfortunately, I cannot show you all the functionalities for time limit. So in the first folder, we can find functions for running the so-called TOST, the two-sample equivalent test, where the equivalent means that two means of two populations differ by a small predefined amount. And inside the folder, there are several methods that provide slightly different modification of the TOST test. And what is important is that we try to automatize also the prerequisites of the statistical test, so the normalcy test and the heteroscedasticity, so the user doesn't have to run them separately. And there are also modifications of the main TOST to account for different implementation of the methodology. And so, for example, to adjust the degree of freedom or to adjust for heteroscedastic inputs. Then we have a function library for the non-inferiority and the superiority test, and a Bayesian approach called the region of practical equivalence. Theoretically, the equivalence is like to test the alternative hypothesis that the mean difference between two measurements fall inside a range. This range is called regulatory boundary and should be fixed by the user. So usually the user checks for literature or by experience this regulatory boundary. And for non-inferiority test instead, it tells us that methodology is as good as a previous or a gold standard. In this case, we usually set only one boundary. And then for the superiority test, to evaluate the superiority of one methodology referred to another, usually we fix the regulatory boundary to 0. Let's example, a practical example. Here we have, for example, the outputs of two equipments or two devices used in a laboratory, or two machines or two assays, or the organic samples. And we would like to test if there is equivalence between the two outputs. In the Python library here, I inserted like a code to visualize what it could be the function calls. Here we can see like I prepared a little scheme where we can see that equivalent testing can be summarized by testing if the confidence intervals or the mean difference fall inside the equivalence region. Indeed, this is the outcome of one of the functions here, and it helps the user to visualize the test. It shows the equivalent regions, so the user has to set the margins, and shows if the active span of the difference fall inside the margin. And also helps the user to visualize the theoretical difference between the mean difference and 0. So we expect that if two measurements are equivalent, the difference is 0. So the user have several information in this graph. In this situation, the active span of the main difference, it is outside the regulatory boundaries, and we cannot conclude for equivalence. Another test I'm going to show here is the region of practical equivalence, that it is a Bayesian probabilistic framework, not relying on statistical significance. It is conceptually similar to the equivalent testing because the user have to set a region of equivalence called rho. And then the credible interval should be enclosed inside the rho if there is equivalence. Otherwise, if it is outside, we cannot conclude that the interchangeability of the devices. In this case, the Python library produces a graphical visualization, but if the sample is large enough, it creates a more understandable graph where the rho is the blue line here, and the credible interval is the red line below here. So we can actually see if the red line is enclosed by the blue one. And here we also the probability density estimation of the difference. Another section of the library works on the receiver operating characteristic and to create the famous 2x2 frequency table that in machine learning is usually known as the confusion matrix. From the confusion matrix, it is possible to extract 34 performance indexes that help medical doctors to assess the goodness of a therapy or a diagnostic results versus the status of the disease. While the receiver operating characteristic is a curve that is shown here and is produced by one of the Python functions and shows the relation between the false positive rate and the true positive rate, at different results. So the Python library, here it is a code snippet and produces more information than the standard rocks. So the Yoden index, that it is the best cutoff, and the key index, and then the theoretical optimum and the MID. So more information for the user to test the goodness for a specific test. Then the performance indexes can be compared through a function call that produces radar plots and automatically can show from 3 to 9 indexes, and user can detect the goodness of a method comparing visually method 1 versus method 2, for example, a new and the old one, or they can also select a graph plot. So here it is the code snippet. For the statistical part, it is possible to statistically compare the ROC curve and also to have some other kind of graphs, for the example, the true positive versus false positive rate graph with the statistic, including the statistic, for example, here on the title. Then we have the effect size and the confidence intervals. Here I'm going a little bit more fast because the effect size is like the a visualization here produced by the Python library that help us to determine the overlapping region between two measurements or two samples from the laboratory, and also produce the non-overlapping indexes, and also other function for the retesting, so trying to address the repeated measurement of laboratory devices or the responsiveness analysis. And here we have also other graphs produced for analyzing the confidence intervals. The most important may be the cat-eye plot, where two methods are compared together, or this stack representation of the confidence interval, because they can help users to determine a regulatory margin, especially for equivalence testing. And then we have the last folder, where we have the Blunt-Altman plot. It is a standard biomedical graph when there are the approximated limit of agreement. And here is the mean difference. This is the standard plot. Usually I took the image from Wikipedia, and this is the novel graph proposed by the Python function. Here we can see there is much more information, and also includes the percentage of points that fall inside the approximate or the exact limits of agreement. These exact are taken as a procedure, a novel procedure taken from literature. And we have also regression diagnostic. For example, we have two measurements from the laboratory. We are running regression, and then we can test if there are influential points. The influential points could be studied by the spread location plot. Here, the user sets the cut distances and then can check which points are outliers, and so can detect if there are problems in one device versus the gold standard, for example. And the last kind of graph is the inherent precision. Imprecision is connected with the laboratory random error, and it is connected with the coefficient of variation. Here it is the graph produced. So we have these regulatory boundaries that are created according to this formula, and these regulatory boundaries are accompanied by a percentage of points, of differential points that fall inside the regulatory boundary. And here we have also the frequency of the points, the mean and the median, so the user can have an idea of the distribution of the data. What is important is that in this function here, we have an automatic adjustment if there is no normalcy in the data, and the interval is adjusted by the Chebyshev formula. So automatically the function changes colors of these regulatory boundaries in case of the adjustment. And so the conclusion, we are going to, here we presented this biomedical related statistical function, but they could also be used in machine learning. For example, if somebody wants to test if two classifiers are equal. And it offers a free alternative to commercial software, because these functions are not still implemented in Python. And in the future, we are going to implement more statistical tests and improve also the visualization, because this library was meant to have enhanced visualization option for the users. So I think I'm done.
Thank you, Mauro. Is your library already being used in like everyday practice, and what is the feedback in particular to the strong focus on the graphical evaluation? Has it been well received?
We just launched the library, and so far I didn't receive feedback because it was like prepared a few months ago. And as there is also, I need to advertise a bit the usage, the possibility, for example, to integrate this function in larger Python libraries like SciPy, for example. So maybe it will be more easy for the user to reach out. And also by the publication of the communication paper, maybe we'll give it visibility to the user. So for the moment, we are using internally in the laboratory, but of course it is already in GitHub, and everybody could use and also report bugs and report feedback.
So thank you very much, Mauro.
You're welcome. Thank you.
And